This is problem 541. It's on page 304. It's just a cantilevered beam. Our goal is to figure out the reactions, and ultimately the purpose is to get the shear and moment in the beam so that later we could perform stress analysis. Now there's a distributed load on this beam. In fact, there's two distributed loads. One is 1,000 newtons per meter, and that acts over a distance of, let's put it below, I guess, 0.4 meters. The other distributed load is half of that. It's 500 newtons per meter, and that acts over a distance of also 0.4 meters, and then we're not interested in what happens after that. Could the beam, or could this cantilevered beam extend beyond? Sure. What would be the load in the beam beyond here, just intuitively? Nothing, right? There's no load out there, so there's no load in the beam. There wouldn't be any stress in the beam. Well, you could talk about the little stress in the beam due to the weight of the beam, but who knows which way this beam's actually oriented. So we won't. We'll just calculate the stress due to the distributed loads that are shown. Now, this is a little different than what we've seen so far, because the reactions are going to be reactions at the wall. And of course, we'll have both a force and a moment reaction. Okay? So now, using a free body diagram, it would look something like this. We'd have the effect of the distributed loads applied at, well, this distance would be 0.2 meters, and this distance would be 0.6 meters, right? Because again, I'm going to take a resultant. So 1,000 times 0.4 is 400. And 500 times 0.4 is going to be 200. Okay? And so there's the resultant loads and where they act. Well, what would you have to do? Well, you'd have to apply a force in this direction of how much? 600. Right? You can do that in your head. That's just sum of forces. What about the moment? Well, there would also have to be a moment. Now let me draw the moment counterclockwise as positive. Okay, so here's the moment. And this would be the moment at the wall. Usually what you do is you make that point A, so you'd say the moment at A. So the sum of the moments would be 0. That would be equal to the positive moment A from the wall, or the moment at A from the wall, less the moment due to these other two loads. So 0.2 meters multiplied by 400 newtons minus 0.6 meters multiplied by 200 newtons. Okay, so the moment at A is how much? Well, all we got to do is add these two up, and that's our answer. Sometimes when I do math in my head, I mess up, so I will rely on my calculator. And sometimes when I do math on my calculator, I mess up anyway. But according to what I've calculated here, it looks like it should be 200. Is that what you got also? 200 newton meters? I think I might have hit a wrong key. Let me make sure. Yeah, I got 200. Okay, so basically the reactionary forces and moments are 600 newtons and a moment of 200 newton meters. I'll try that again. Okay, so there are the reactions just from statics. So far, so good? All right, now we'd like to make shear and moment diagrams. So let's do that next. I should have made this bigger, but that's okay. Video's still on, okay. All right, shear diagram in newtons. Let's see, so we begin, let's see, if you imagine cutting the beam here, the 600 Newton force from the wall is pushing up on the beam, and so we need a shear in the positive direction, which is downward, in the amount of 600 newtons. As you go along, less and less shear is needed. In fact, by the time we get to this point, remember what the reaction was? It was 400. In fact, by the time we get to this point in the beam, we only need a shear of, let's just put it here, of 200 newtons. right? Because the distributed load is providing 400 newtons of the force needed to keep this section of the beam in equilibrium. Okay? Now, this next section, that is, what did I say, 200 newtons? Okay, so let's see, is that right? Yeah, that's right. 200 newtons. Now that 200 newtons is distributed, so basically it's going to bring the shear to 0 at the end of the beam, but of course it does so gradually. Okay? How about the moment diagram? Again, the moment is just the integral of the shear. Okay? So now I'll ask the same kind of question I did last time. Well, actually let me start off with it. Should the moment line that I draw here be concave up, concave down? What do you think? Is the moment increasing or decreasing? Well, let's think about that first. Imagine cutting the beam somewhere out here. Shear is still down like this. What would we have to do with the moment? You have to be careful here. You have to think about it. Because there's actually a beginning moment, right? The moment begins at 200 Newton meters. Now this is the moment applied to the beam. So let's make a free body of the beam over here. Basically the moment from the wall is 200 Newton meters, right? And so the amount of moment required on this side of the beam where we've actually cut it is going to be negative. Does that make sense? So we have to actually start, I should have done it like this. We have to start down at negative 200 Newton meters. That's really where this begins. So we're going to move from here. Now, notice that as you go along and there's more and more moment of this distributed load, the amount of moment required to keep the beam in equilibrium will decrease. Okay? So let's see if we can figure out how this goes. First of all, let's figure out how much the moment changes. So let's figure out this area. Well, let's see. The easy way to do that would be 600 times 0.4, which would be the whole thing, less this upper triangle, which would be 400 times 0.4 over 2. I should have typed that in as I said it. So 600 times 0.4 less the difference, 400 times 0.4 over 2 is 160. So this area is 160 Newton meters of moment. Well, that's not going to take care, that's not going to provide enough to resist all 200 Newton meters that the wall is applying. Okay? So we'll end up about here at 40 Newton meters. Does that make sense? Because the distributed load is only providing a change of 160. Okay, remember this area here is just change, right? It's not the value of the moment itself. Now let's ask the question, should we go concave up or concave down? Well, we started out at 200 and we're taking away from it. That's what this is doing. It's taking away from it and moving us up. Okay? But we're taking away quickly at first and then slower as we go along. Concave down, good job. Okay. Again, my drawing's not real good because we need to come away from this point doing the same thing, right? Basically, the rest of this area should subtract the rest of that moment because out at the end of the beam, there's no way we can have any moment at all. So the loads at the end are 0. So we hope we come to 0, right? And we have to go concave down again, but unfortunately I want the slope on this side less than the slope on this side, but my drawing's not very good, and hopefully it'll come to 0. But let's make sure of that. Let's calculate the change. So this is 200 times 0.4 over 2. So 200 times 0.2 is 40. Sure enough, it works. It takes care of the rest of it. Where's the worst place for this beam? At the wall. Both the shear and the moment are highest at the wall, so that's where we would expect failure, which intuitively makes sense. Questions, comments?